Hey, good morning, everyone. We're going to get started now. So I'd like to welcome everybody to our August webinar around steppers and servos and VFDs. And I see the title is Inductions and Steppers and Servos Oh My. So obviously, Mr. Rob Willey, one of our presenters today, has a little sense of humor. So at this time, I'd like to turn it over to Rob and get started on our webinar for today. Rob?
Yep, and I'll jump on camera here really quick. Hello, everybody. And so, yeah, I'm Rob Willey. Hello. And joined by Bruce Ellis. I also see that Steve Stewart and Steve Updike are also on the call. And yeah, so just wanted to start off with a little lighthearted. We are going over different types of motors. And so here's the agenda in front of us. So I'm going to start off talking about why we're doing this and go into how each of the different technologies work. And we would like to have an open discussion on where these can be used. We have a lot of information in this, so I'm going to kind of move quickly as to why we're doing this. So in a nutshell, motors take electrical energy and they convert it to mechanical energy. There are different application requirements. Sometimes we just want a fan to spin. Maybe we want to add some positioning to that. Maybe we don't need as large of a motor for that application. And so there's different ways of going about that. And so we're going to cover the three most common types of motors, which are induction, stepper, and servo, and where and when they should be used. And then we can talk about where some of them actually overlap. And that's where you'll have to decide, based on cost and, your overall throughput of your machine. So all of those really come into play. Now I'm going to turn this over to Bruce. And Bruce, you tell me when to advance the slide, and we'll start with induction motors.
Okay, so obviously there's a Wizard of Oz thing going on here. So what I don't want to do is take a lot of time. I only have a few minutes. So in my class, typically I spend about an hour on this. So if you get anything away from these three slides, the first thing is for power flex, you need to understand the speed, the torque, and the speed range of your application. So when you look at the slide here, oops.
That's me. Yeah, I'm trying to get a pointer in case you need me to point out something.
Okay, the number of poles. So the number of poles in an AC motor are directly related to the torque and speed accuracy. So when you look at the diagram on the lower right, what we're looking at here are AC coils. These coils are housed in the stator. Why are these important for an AC motor? It's because if I think about an application where I need full torque at zero speed, I'd better have the most number of poles I can in the motor. So if you look at my slide, I have a 6-pole motor called out here. In the picture, I have 2 and 4 poles. Why is that? So the most commonly sold motor for induction is a 4-pole motor. It's a combination of speed and torque. If you think about it, if you look at my first 2-pole cross-sectional area of the motor there, that motor is going to run the fastest. There's a north and a south pole. We only have 2 poles. That'll have the highest speed, but the lowest torque. If you look at the 4-pole, now we have 4 poles. It runs at 1800 RPM and gives us a blend between speed and torque. The 6-pole motor has the largest, greatest torque for an application, but it runs the slowest, and that's 1200 RPM. So why is that important? Again, that ties back to my opening statement of if you know the speed, the torque, and the speed range required for an application, you would pick the RPM or pole structure of the induction motor based on what you need to spin the load. Lower pole counts, higher speeds, higher pole counts, more torque. The second thing we have to talk about on an AC motor is frame construction. Why is this important? So if you look at the diagram in the upper right, it shows a fan attached to the rotor, which is the spinning part of the AC motor. That fan draws air in across and pushes it across the motor frame. Why is that important? We need to cool these poles off as they're running full current or for full load. So for a totally enclosed fan cooled, which the fan is attached to the rotor, it's designed to run full current, full load at half base speed. So again, back to our 1800 RPM motor example, 900 RPM to 1800 RPM for a TFC frame construction is going to be the speed range to run full current, full torque. What happens if I run that at 100 RPM? That motor is not going to last very long. It's going to overheat. That brings us to our second motor frame construction, totally enclosed and non-ventilated. This is where we do away with the fan that's mechanically rotated, and we actually put more steel into the frame of the motor. Why do we do that? We have it act convection cooling. It acts like a large heat sink. For this motor, we can get higher or lower speed operation with higher torque. And the typical design factor around what you need to look at on this motor is the turn down ratio. And on my slide, I have 4-to-1, 10-to-1, and 120-to-1. I'm going to pick 10-to-1 to make my math really easy. So if I have an 1800 RPM motor, I have a 10-to-1 totally enclosed non-ventilated motor, I can run about 180 RPM at full load, full torque. So that motor can cool itself from 180 RPM to 1800. Then the third one I want to talk about is totally enclosed force ventilated. So if you look at the picture in the upper right again, we take the cooling fan off the end, we put a fan on that's driven by a separate motor, and we constantly blow a volume of air across the frame. That motor can run full speed, full torque all day long, very slow, very accurate. So those are the three basic motor frame types. So go ahead and advance it, Rob. Thank you, sir. So now that we talked about the motor a little bit and which one we would pick for different applications, let's talk about the drive. We have our drives broken up into two groups. That's component class and architecture class. The component class is the 520, which Rob's pointing to there. The architecture class is the 750 above it. Those are the two we're going to talk about today. As you look at this picture on the right, the portfolio, we have a drive that goes up to 5,000. Actually, we have 10,000 horsepower drive, which is our medium voltage, all the way down to 4M, which is fractional horsepower. But we're going to concentrate on these two due to time constraints. So the 520 series is a general purpose speed regulator. We can regulate speed down to RPM, 90 RPM with an encoder. Without an encoder, we can regulate speed to about 300 RPM. Great general purpose drives for fans, pumps, conveyors, things that aren't heavily loaded. What motor would I pick? It would be a totally enclosed fan cooled or non-vent motor with 2 or 4 pole construction, which means 3,600 RPM or 1,800 RPM. If I look at the 750 series drive, it regulates speed and torque down to 2 RPM with an encoder or 90 RPM without an encoder. And the kind of design philosophy from the 750 series, one drive to do all applications. We can drive any kind of motor, any pole count, any RPM structure. And that would be any of the 750 series drives. Next slide. Okay, so how would I apply these now? Again, that's just a kind of a quick run through of the motor and the drive. What I would do is think about, again, at the beginning, I said, if you take one thing away from my 3 slides, for power flex VFD with an induction motor, you got to think about the speed range, the torque required, and then the speed regulation accuracy that you need. So what I would do is choose a motor based on current, size it off full load current, not horsepower. Why is that? Our selector guides, if you use Proposal Works or our online selector guide for the PowerFlex, we break drives up into 2 classes, normal duty and heavy duty. What we don't tell you is all the charts are based off a 4-pole 1,800 RPM motor. So what happens if you have a 6-pole 1200 RPM motor, and you go to the selection charts and base it off horsepower. As your pole count goes up, your current required to drive that goes up. You may not have enough full load current in that drive if you choose to drive based on horsepower. So for that reason, I always tell everybody, if you need full torque, slow speeds, make sure you size your drive on full motor load amps, not horsepower. What's the definition of normal duty and heavy duty? It is variable torque load for a normal and constant torque load for a heavy duty. I'll let you read, there's different overload settings for both inside of our drives. And I just want to kind of cover real quick, I have about 2 minutes left, constant torque versus variable torque in our application matrix that we publish. Constant torque is the graph on the left. What the graph's trying to tell you is, doesn't matter what the speed you're running the motor, the torque demanded to drive that motor is constant. So if you look at the second red box I have below in my application matrix, I highlighted a compressor application. We're running actually a reciprocal piston driven press. If you look at the speed torque characteristics, the box check says constant torque, which means it needs the same amount of torque no matter what speed you run it. It talks about the speed range of 10-1. We talked about that before. Basically, you're going to need a motor that can run between 180 RPM and 1800, and you need speed regulator type. The second type of load would be a variable torque load. We could select a normal duty drive. And if you look at the graph below variable torque load, is exponential rise. I don't know where your pointer is there, Rob. The faster you spin that load, the more torque it takes. Good example I have is the first red box, and that is a fan. What are we moving? The load is air. The faster we spin that load, the more torque's that required. So if you look, variable torque box is selected, and the speed range is 4-1. So on that particular application, we need a motor that can go full torque, full power from 455 RPM to 1800. So which drive would I pick for these? Anything 10-1 on down, you can use a 525 on or 520 series. 10-1 on up, PowerFlex 750 series drive. And those two the slide before kind of indicates that. So that application matrix, it's a 2-page PDF. I gave it to Rob, and we can send that out so you can reference that chart. I think there's about 75 applications on that describe the speed torque characteristics. So again, PowerFlex, we regulate speed and torque. For your application, you need to know where you need your torque and what's the slowest speed range or speed number that you need. And that's what I have.
Awesome, Bruce. That was really good. So I'll take over. There we go. So now we're going to talk next about stepper motors. So this is really in a stark contrast to what Bruce was just talking about. Really, you're going from a quarter horse on up, for mechanical energy. Stepper motors are really designed for less torque, but you need some positioning capabilities now. And so it's a brushless motor, and the current to that motor is always constant. So the advantage is you get full torque at standstill, which means you can go and try and move that motor, and as long as it's not getting any additional pulses, it will stay in its position. Again, designed for low torque positioning applications. So you'll see in this speed torque curve, we're measuring in ounces per inch. There's other applications where we talk about later in servos about Newton meters and foot pounds. And so really we're looking at how many ounces of torque we are applying an inch away from the center. Is really how we're measuring this. And so what happens is as this motor is running at a higher speed, you're going to get less torque. Looking at this speed torque curve, at 0, we have full torque. And as that speed increases, say to 600 RPM, when we're in 24-volt mode, that torque is dropped by over half. So it is really important to look at like your available power, because at higher voltages, all in DC, you can get more torque out of it. And then obviously as we get to our max rated speed of these motors, we lose a lot more torque. So getting encoder feedback is purely optional. Typically, I don't see that being used, but we do offer steppers, and I'll talk about our product offering because it typically is not a Rockwell automation product per se. But if you've ever seen a 3D printer, that is a great application of 4 different stepper motors. One of them is usually on a ball screw, moving the printer jet up and down. It's very precise. It can move at low speeds. And then you also have 2 steppers that are going to drive the XY belt. Usually one's for the table and the other one's for the Y-axis left, right. And then there's another stepper motor that actually provides the filament. And so they all run at different speeds together in a coordinated fashion. So this can be extended out to small robotics. It can even be done on CNC milling, some welding equipment. But some of this might overlap with servos because we are looking at some speed, but we're also looking at position. So how does this work? How does the stepper work? So going back to what Bruce was talking about poles, in this case, we're looking at a 2-pole motor, and the poles are the rotor is turned based on energizing these phases, kind of like the stators. And so we'll move this motor based on those phases, and it'll draw the south pole. So you'll see the B phase gets energized, the second A phase gets energized, the second B phase gets energized. So that's really, in a nutshell, how these work. You're sending a pulse to that motor to energize each phase in succession. Now, on most steppers, they have 50 teeth. And so it looks like these little mini poles, and then all of these different phases that will get powered on in succession to turn that stepper incrementally. And then you can do half stepping, where you power on both phases to move these teeth in between each of the stators. So that's how you get that kind of accuracy on a stepper. How is this controlled? Now, we offer products from AMCI, and steppers are driven by a driver, okay? So kind of like a motor gets driven by a PowerFlex drive, steppers will have a driver that will send out those pulses to the stepper motor. We offer, like in this case, this is a stepper motor that has the driver integrated and just gets a simple Ethernet connection to it. And that can be used, you can send messages to it, commands to that stepper to move to a certain position at a specific speed. On our MicroLogix and Micro 800 controllers, this can be achieved through, on our DC output processors, we have what's called pulse train output, which are high-speed outputs. And we use, in the Micro 800, we use motion commands to drive those motions. So you would wire 2 outputs, one for step, the other for direction, to one of these drivers, and it will send, those commands will send pulses to it. On the MicroLogix, it's just an instruction called PT. And what you'll do is you'll say, okay, send this many pulses in this length of time, and the stepper will react in that fashion. On Compact and ControlLogix, we offer stepper modules currently on all platforms with the exception of Flex and 5069. So we can do Point.io, we can do the 1769, so you'll see some of these modules here, and also in ControlLogix. And so these can be used to tie into these steppers, or if you want to use standalone steppers or integrated steppers that have Ethernet, you don't need a motion-enabled compact or control logics controller. What you can do is they'll have their own add-on instructions that you will put into your code to drive these steppers. Not really seeing a lot of these out in the field, but I wanted to make you aware of it. I've done a few applications with some customers where all they need is just some simple positioning with low torque. So that's my section. I'm going to go ahead and turn it over to Steve Updike, who's going to cover servos.
Okay, servo motors. The most common today are the AC brushless servo motors, although there are still some DC servo motor manufacturers out there. Servos provide stable torque at higher speeds. They have higher speed with precise positioning as compared to a stepper motor where your torque drops off as speed increases. They are closed loop with encoder feedback. A lot of the applications are large robotics, high-speed CNC milling, product dispensing, precision conveyors, food and beverage, and automotive. Now, the servo motors have a constant field that's provided by rare earth permanent magnets. So even with a motor with no power on it, it still has the capability to provide a field. If you were to take a servo motor and tie the motor leads U, V, and W together, the shaft would actually lock because those magnets are providing a field. And that allows them to provide precision positioning throughout their entire speed range. They also have encoder feedback. With hyperface encoders, you can get like 2 million counts per motor rev. Digital servo links are like 200,000 counts per motor rev. And the A-quad beads with a 2,000, they look at interpolate the rising and falling edges, and you can get 8,000 counts. So you can get positioning based upon the encoder you select. Go ahead, Rob. One of the key things to the servo motor is the controller. You know, what does the servo motor have to do? So the servo drive provides the power to the motor. It interpolates the feedback from the motor for both velocity and position. And it receives a command based on what your application is. And we'll talk about that more in the next slide. With servo motors, a lot of times you end up with a gearbox. Because a servo motor is servoing, which means its loops are always active, inertia ratio comes into play where it needs to be able to move that load constantly, even at zero speed. So a lot of times you end up with the gearbox as it gets your inertia ratio down, and it allows you to go to a smaller motor because the gearbox multiplies the torque of the motor, but you do sacrifice speed. So things like belt-driven conveyors, trains usually end up with a gearbox on there and a smaller servo to get that inertia ratio down. And cost kind of comes out the same because you have a smaller motor, but that gearbox gives you the torque you need. Okay, next slide. Now, when we talk about servo amps, this is one of the things we spend a lot of our time on is what does the application have to do? We have standalone indexing amps, which means that amp can run the motor without having any PLC interface on it. They have program moves in them. They can be run via the I/O from a PLC or just select the switches and push buttons. And they can generate signals that tell you they're done with their move, they're faulted, they're ready. So they give you a little feedback that you can use in your control system there. They can also run on the PTO output, just like the steppers do that Rob just talked about, and take that step direction input. So say you have a application where a stepper doesn't have the speed you need, but you would like to use like an 850 servo or 850 micrologics. you could take and use that PTO output and run it into the standalone drive and get the higher torque and higher speeds you need without buying a more expensive front end. And we're going to say the most common thing we have is our integrated motion. You need a motion-enabled PLC. They usually have an M at the end of them. They have all the programming with blocks set up in there, so they're very easy to configure and write the logic for. There are many motion commands you can use besides just move from point to point. You can do camming, gearing, coordinated motion. You can play with torque settings, say you want to limit torque. So there's a lot you can do with the integrated motion platform. And they also still support circles for the older stuff out in the field on control logic. So servos kind of do everything that an induction motor could do at a stepper, but it's at a much higher cost. And the larger the horsepower, the more the cost goes up. But kind of what we want to talk about is, you know, what could you do different than using a servo, using a stepper motor or an AC motor to kind of make your applications more efficient? Turn it over to you, Rob.
Yeah, no, and so good stuff. Want to make you aware of some of the product selection tools that we do have. So Proposal Works to help put together, you know, a complete motion or motor system. We also have Integrated Architecture Builder, which you can use to validate your system. So if you have a certain number of axes, especially in motion, you have to have the right size PLC to control that. We also have Motion Analyzer Online. So if you know your mechanicals, and this is where it's a good idea to have your mechanical guy help. But if you put in all of your devices that you're moving, weights, your material, Motion Analyzer Online can help you select the right size motor based on your speed requirements and your load. And then there's us. There's the Rexel product specialists. Appreciate everybody's time.